evaporation.
Well, hello everyone. I'm Petros. I'm currently a research fellow at the University of Bologna in Italy, and I completed my PhD at the University of Bath in the UK. And as it's my first opportunity to share my work in an international audience after COVID, I will try to squeeze in as much information and key findings I could from my work. And you will find more information in the respective publications, and there will be links on the screen. Um, so blue spaces. When we talk about blue space, we talk about rivers. We could talk about small ponds. We can talk about seas, irrigation systems. But in this work, I'm going to refer to basically water ponds. So that's number one up in the screen, and not the rest. So we're talking about static water bodies instead of dynamic ones, which are have different physics and different mechanism included. So blue spaces are important for cities, for people, because they actually benefit health and well-being. There's actually recent research around this, and people found that cities that live close to water bodies, they have decreased premature deaths, they have increased physical activity, social interaction, but also blue spaces affect and promote biodiversity. This is a report of 2021 from the British Ecological Society that states that blue and green spaces offer significant potential in moderating increased summer temperatures. And the question is, do they? We know a lot about green spaces. Almost most of the current literature is focused on green spaces, but there's really little research around blue spaces. Um, so in our review paper published recently, we actually highlighted these gaps concerning the evaporation effects, the nighttime situation. So when during the late summer period, water can be warmer than the surroundings. That can be important in heat stress. Also, the effects of increased humidity and the impact of geometry and design. So we really don't know, don't have guidelines of regarding blue spaces. Um, so the aim of the work is actually to develop numerical capabilities to systematically appraise blue space effects in an urban context to mitigate the adverse effects of the urban heat island. And the focus will be mainly on the impact that blue spaces have on the temperature field, the water vapor field, airflow and turbulence. So just to put into concept, talking about blue spaces, we can split into three phases. So in an early morning, when we have relatively moderate stability of the atmosphere, we have some evaporative fluxing going up and some moisture content adding to at pedestrian level. And during later in the day, in the afternoon, where we have the ground is heated, we have this convective fluxes going upwards. That's we call convective instability, and we have the maximum evaporative flux and really little moisture content at the pedestrian level. And during the nighttime, when we have this more stable atmosphere or near neutral, actually, the question is if this we have a warming effect and this increased moisture content, if this is going to have an adverse impact on heat stress. Um, so the model itself, we treat the ambient air as a mixture of ideal gases, that's water, vapor, and air, and we model it as incompressible fluids. The buoyancy, we solve it with the Boussinesq approximation for temperature and water vapor. And the evaporation model itself treats the blue space to be at rest, so there's no wave, and isothermal, so same temperature horizontally, but also vertically, so we don't solve the internal motions of water. Um, the evaporation is treated as a thin film assumption, so we have a surface that actually can evaporate infinitely, and I'm going to explain why this is it's not a problem in this case. So water vapor is treated as an active scalar. It interacts with the flow, and it's impacted by the flow as well. And the model is applied as a set of boundary conditions in the model. You can find more information of my colleagues' papers that they actually started to develop this model inside a washing machine they were studying. The numerical approach is run, so we have steady state simulation. We study snapshots in time, so we're not worrying about like dynamic aspect, just instances in time. That's why an kind of infinitely evaporating surface is okay. It works in our case. We compared three different turbulence models, concluding that the RNG KF was the best. Everything is implemented in OpenFOAM, which is a CFD toolbox, and it's based on the existing solver in the library. We validated the model against both a single building and a 3 by 3 building array, and also we evaporated crudely evaporation from small scale water surface. And I say crudely because actually there's a lack of benchmark cases of wind tunnel studies that study evaporation and heat transfer effects within an urban context. And this actually call for future work for everyone. The simulation setup, we chose this 7 by 3 building array, and we have replaced the middle building to create this open square with a water body. And the number of the buildings was after sensitivity analysis that we saw that the number of upwind buildings really don't affect the results at the area of interest. The temperature of the water, so we simulated two cases, a cooler water body and a warmer one. So we have two temperature degrees difference, either cooler or warmer. And we focus on the local convection regimes within the area of interest. That is a mixed convection with a Richardson number of 1.1 and a forced convection regime of 0.04. What this means is that in forced convection, basically air and the inertial forces are stronger and dominate, whereas in mixed convection we have buoyancy also playing an important role in the results. And regarding the shape and the size, we chose to decrease the size gradually and also elongate the shape. And we did the specific configuration to avoid any part of the water body being exposed to the prevailing wind. We want to avoid this case. So initial results considered this is a mixed convection case. So we have on the upper figure we have a cooler water body and a warmer water body. You can see how this warmer case, when buoyancy is important, can create this upward motion that goes above the canopy level. And this is the situation in the downwind canyon. So this was the area of interest at the left. And here you have the downwind canyons that actually you have a breaking of the skimming flow. So the warmer water body in the open square create this upward motion that drives the flow from the downwind canyons as well upwards. And we are currently studying this an ongoing work if this actually is a potential pollutant removal mechanism from water bodies when they are warmer, of course. So what about the impact of size and shape? So we can see here we have the baseline scenario on the left. There is no water body. This is the airflow structure. And then we have the introduction of a warmer water body of a square water body, basically. And we have this upward motion. So we want to see by decreasing the size gradually if we can have where is the threshold that this upward motion actually is trapped within the canyon and does not leave. And here we can see obviously there is when we decrease it below like an eighth or a 16th of the initial size, we get some trapped of the flow inside here. So during warm summer nights, the key message is that inadequately sized water bodies can actually may worsen heat stress in cities. This is the horizontal scale, at the horizontal level, temperature, water vapor contours. And we can see again with different water body sizes how the effects are spread. And the important here is that we introduce this effectiveness, which is basically a measure of the total influence, the area of influence, so at which level the water body effects are felt, divided by the area of the water body. And we can actually see that although the magnitude, like the most cooling here is that the larger water body, the size is larger, the effectiveness is larger when we have a smaller water body. So it means you can spread more compared to a larger one. So here we saw that blue space effectiveness really depends on the local velocity field, and that several small water bodies may be better for widespread cooling. Here, in the case of a different shape, again with cooler water bodies, we can see that the magnitude is larger at this shape and not in the square again. And the effectiveness is the same because here we don't have a different. We have the same size, so the effectiveness is basically measured by the magnitude of the effect. And again, here we found no direct analogy between blue space shape and the magnitude of its effect. So takeaway messages: please consider the influence of local convection regime when we study blue spaces. It's really important and really guides the way they function. And also promote the study of the whole diurnal and seasonal cycle of water and blue spaces in cities. And large water bodies may be better suited to promote this upward transport of heat and maybe pollutants, and small ones. But if if they're smaller, they can really worsen heat stress at the pedestrian level. And the small ones are better for localized cooling, whereas there's no direct analogy between the shape and the magnitude of a water body's effect. I think that's it. I think I'm on time. I didn't see your the signs. Thank you.
Questions? You have a question? Yes, please.
Thanks so much for the presentation. It was really great. Did you study at all the surface conditions with regards to whether it was disturbed water or water that was just an enclosed body?
You mean the water itself, the water body itself, the surface of the water body is at rest, so there's no movement.
Do you have more questions? If not, we will move to our next presentation. Okay, our next speaker will be Bing Chen, talking about multi-scale